Okay, so beginning with chapter 9, covering the moon and Mercury, which are shown to scale on this first slide. The moon, by the way, is on the left. It is smaller than Mercury. Significantly smaller, but they're both closer in size to each other than either of them are to Earth. So, kind of compare what it means to be bigger, right? And they look pretty similar, you know? The moon has greater albedo, to use a term that we just were introduced to in the previous chapter, which means it's more reflective. Part of the reason it's so bright in the sky, by the way. And, the Mercury has more of this sort of like almost like cast iron look to it, due to some chemical interactions. But what they have in common is, kind of large flat areas, lots of craters. Just they have, some pretty similar aspects. Um, the moon has defining regions that are noticeably darker and kind of look like they're filled in. Those are the lunar mares. So it's a and thinking about the saying the singular is Maria. So it's a yeah. So one lunar Maria, which is spelled like Maria, and then the plural is mares. Mercury over here has these lines known for its cliffs, but other than that, you know, the the impact craters are really quite similar, right? So they really share that same cratering surface. Okay. So our plan is to talk about the moon, survey its surface, make sure we understand what we're looking at and are the explanations of those surface features. Talk about the best and current theory of where the moon came from. Talk about the history of exploration. I'll go through it a little bit quickly, but it's interesting stuff. And um, how it's related to Earth, although we've talked about that some already, right? Things like phases and tides. So, that will not be a main focus. Then we'll turn our attention to Mercury, right? Not another moon, but actually a planet, right? Key features, composition and crust, the surface, the atmosphere. So kind of a similar approach we took to Earth as a planet, right? All right. So some of the features on the loon, on the lunar surface or on the moon. Catenas, craters, highlands, Maria, moon dust, riles. All right. Lots of terminology here. Okay. So at surface features that are created by geology, right? So geological phenomenon like volcanic eruptions, um, cooling, right? Things like that include the Maria, the highlands, and the riles. Surface features that are created by space, right? So interactions with space, incoming objects, craters, moon dust, and catenas. All right. So the highlands are light colored, hilly raised regions with light silicates. They floated to the surface when the moon was molten and undergoing differentiation. The Maria, on the other hand, are flat, dark areas formed from lava flows, where lava broke through later in the moon's history and filled in large regions. Some is filling in a big crater, but other times filling in multiple craters and creating a large flat area. So when you compare the two, you see the highlands are heavily cratered and the Maria are not. Okay. This is that same aging comparison that we used as the poster child, so to speak, of dating using cratering in the solar system, because it can be used throughout the solar system, but the moon is kind of the baseline comparison. And the moon is where we can confirm the ages with rocks because we've gone and collected them. And with the rocks, we use the radiometric dating technique for confirmation. Okay, so which is older? Who remembers? Are the highlands older or the Maria, the lava flows? All right, thank you. Alexander Ace. Both said one. All right, Anthony agrees. Absolutely. More heavily cratered means older. That's how we date with crater. That was what I was checking. See if you remember. Right? So an altimeter is placed in orbit around the moon. This is measuring elevations. It uses radio waves to track the elevation changes on the moon's surface below. Which of the photos below correctly shows the elevation of the highlands and the Maria? Okay. So I'm going to not check for responses, but if you want to put in an answer, think about it yourself. You have a moment. But in the interest of time, let's look at our answer right here. We're going to see the bumpy highlands because of all those craters and the rims around them. And we're going to see the flat Maria lower down. So highlands is not just a name given. It does actually represent that they are higher, and the Maria are both lower and flat. What are riles? Well, they're long, thin ditches that are stretching across the surface. We see one shown here. Okay. Notice that it does look like a ditch in that it has two rims to it and a kind of long, continuous lower portion, almost like someone troweled it out. Okay. The one shown here, the Rimi Cauchy, a straight rille formed by the surface pulling apart and the ground sinking down into the gap. We have similar geological features on Earth called graben, such as Death Valley. So where you have a pulling apart of the surface involved with plate tectonics on Earth, but on the moon involved with early stages of the formation and the sort of like solidifying of the surface, the final stages of the moon's formation. All right. Here's another one, the Rima Sharp, a sinuous rille. This one was formed by flowing lava rivers or perhaps collapsing lava tubes underground. So although the name is given to both of them, both the rille like the Rima Cauchy and the Rima Sharp, which is the opposite of sharp, right? It's quite instead it's like should be called the Rima Wiggly, but it's named after a person named Sharp. But in both cases, for the actual origin of the structure could be quite different, you know. So the name only represents the appearance rather than what made them. But they are a defining characteristic of the surface of the moon, the surface of the moon. Here you have one more here, and Arcuit, as far as if I'm pronouncing that correctly, Ryle. This one formed by heavy lava that actually weighted down the ground underneath it, and sort of compacted it, and as it cooled along the edge of the Maria, so it created this ditch because of the greater density. And our last feature, at least one of the last ones, that's because I guess we still have the space-based ones, right? Yeah. We have the catenas, all right, and they're lines of craters created by broken fragments of impacting objects, right? So they are coming from space, right? So we covered our last of the geological features because we had the highlands, the Maria, and the Riles as geological. And this one is from an impact. So if you had basically something that had broken into fragments, so each object would have entered the essentially the gravitational region of gravitational influence of the moon, and you can imagine a bunch of sort of like parabolic paths that are coming down into, and all hitting at slightly different points. This one's called the Anki Catena. It's actually not on the moon at all, but there are some on the moon. But this was I guess, a high quality image that they decided as a representative one for catenas. The moon is covered in very fine dust. And so that came to mind actually when I was talking about the Ryle a minute ago, the one that that was formed by the lava, because lava being able to cause the ground to collapse underneath it might be hard to imagine on Earth unless the ground is, really soft. And that's what the ground is like on the moon. The whole surface is just this very fine dust. And that has to do with, you know, the fact that it's never had a atmosphere to compact rocks. It's never had the processes that the geological processes that we have on Earth that are facilitated by the water cycle, the processes that create sedimentary rocks, let alone, all of the rocks that are created through, lava flow and cooling lava. And then, those getting broken up and so on. And and then a lot of the metamorphic rocks that are created because we have these plate tectonics that are pulling things underneath and allowing them to get pressurized and heated up and turned into solid chunks and then pushed back up to the surface. Instead, the surface is just there, exposed to space, exposed to the energy and all of the objects coming from space. And that means that it's just a bunch of pulverized rock, an incredibly fine sand covering the entire surface. That's called the regolith. We also say that Mars is covered in a regolith. So the craters impact that fine dust. So all the craters aren't craters in some like hard packed material, although the Maria might be a more dense material, but the highlands are not. The craters are just impact bowls made by the objects impacting the surface, the body, right? The moon being the body. Craters look the same as the short-lived craters that we talked about that exist on Earth. So crater creation occurs when the asteroid comes from space, gets pulled into the gravity of the world, comes down to the surface, and hits the surface. It then gets vaporized. Okay? There is ejection, which I think is actually missing. The picture is. Basically, the rock gets thrown up in all directions. Because it got ejected, not, and thrown off in all directions, only some of it is able to fall right back down. So there's some refilling back into the crater, but all the stuff that got ejected to the side, right, depending on its velocity, will achieve a certain range. And that's why you have the ridge forming, right? So the ridge is forming because of the settling of the material, as well as the release of energy that pushed some of that material directly to the sides. There's a link to a video that you can see about the impact cratering process. I won't play it in the interest of time. I want to get through as much as we can. I will point out the interesting idea that a lot of people ask, and I remember asking this myself, but why are almost all craters perfectly round? Don't asteroids enter at angles other than straight down? And the answer is yes, asteroids enter at all kinds of angles, but with some few exceptions of very, like low angles. So an asteroid that's coming in almost like skimming the surface, that can create a crater that's not round. The vast majority are perfectly round, even when they come in at a wide variety of angles measured relative to the vertical, because the shape isn't predominantly, dictated by the angle of impact, right? Except for, like I said, a really extreme case, but instead by vaporization. In other words, it doesn't matter what angle the asteroid comes in at, since it is blowing up, and that energy release will always be symmetric. That's why the impact craters are circular, because of the importance of the vaporization process as opposed to just the impact itself. And you could see that if you imagine, what if you wanted to simulate this with smaller objects, right? Well, if I like throw a rock into a sandbox, it makes a big difference what, kind of like path or dent or crater I make in the sand when the rock impacts it, depending on how I throw that rock into the sandbox, right? If I drop it straight down, I get something that looks like a crater, right? But the rock doesn't vaporize, it's just still there, right? It'd be sitting in the middle. And so that's not a good analogy for these impact craters. I would need something that like actually like breaks open. You could maybe do it with like a water balloon, right? Where that water like gushes out, except for the, kind of the fact that it would also flow and end up creating some little troughs from the flowing water. But if you had something that could pop and blow up, and that would push the sand out of the way, that would then you would be able to show that, despite coming straight down or at an angle, you still almost always get a circular impact. The names of the crater features include the floor, which is just the interior of the crater, the walls, that's the, just the edge as you come up from the floor. When you reach the top of the wall, that's the rim. There's usually a central peak that occurs because of material that settles straight back down. So there's kind of a little bit of a rise there in the middle. Outside of the rim, so beyond the rim, is the ejecta, all the material that was able to fly out and sort of, leads to that gradual downslope. And then you have the rays that point away from the rim as well. All right. So looking at lunar mountains, when you see something like this on the moon, this is not made from volcanic effects or some sort of tectonics. Instead, it's just the peak of a crater. It's just a pile of that regolith that settled down after an impact. The rays that are formed from ejecta leaving the crater are most noticeable with the biggest impacts. They're quite subtle with the smaller ones, as we saw actually in the previous image. But for the really big craters, we see the rays form. And it's the lines of ejecta that sort of coalesce into these particular paths. I'm not sure of what process sort of causes that, because it's not like it's an atmospheric effect. So it's not a flow, but could be a static electricity that kind of causes them to not get evenly distributed. So when you look far enough out, the ejecta ends up concentrating kind of as it falls, as it settles down. But I'd have to look into that more. So craters, especially the deep ones, create shadows that can cause significant light variation between regions inside of craters versus those outside. If you imagine the path of the sun going over a crater, and you have your direct line of sight with the sun shown here, then you have, right, for the deepest craters at certain latitudes, because remember how we talked about, the peak altitude of the sun depends on the latitude of the observer. Well, that's going to be the same for the moon. The moon has very little axial tilt, but that doesn't mean that, the peak altitude doesn't change. It just means that there's just there, you don't have to do that further calculation to find the peak altitude at different latitudes. You just know it's, going to be equal to your latitude. So, if you're really near the pole and you have an equator, or you have a crater near the pole, and the sun not reaching a very high peak altitude because, the angle between the vertical and the location of the sun is essentially equal to the latitude because of the lack of axial tilt. Well, then you're going to have a region that is permanently in shadow, right? Because this, you could think of this as representing the highest point throughout the year, which really won't vary. So it's just every lunar day, because again, no axial tilt, so no seasonal variation. And if there was, by the way, if there was, the moon did have significant axial tilt, even though it orbited us, it still would, then have the seasonal variation because it would, still have the sun, passing over it. But without it, it doesn't. And so, every lunar day, and lunar days are long. They're around 15 Earth days long, but you would have, the sun rise and set and just not cast any light into this region. So it remains permanently in shadow. So when you get up to the poles, if you have a deep crater at the pole, you could have a large region that just doesn't get any light. Okay. And the relationship between them is found by just thinking about a right triangle, finding the depth and the height to the rim. So the angle above the horizon for an object in the sky is called, well, its altitude, right? So hopefully you remember that back from chapter 3 or 4. All right. And which function? You're not responsible for this, but it would be the tangent because it'd be opposite over adjacent. All right, so on to the origin of the moon. Although I will point out that this idea of craters constantly being in shadow is a popular idea with current moon science and planned exploration because of some craters near the poles, including one called Shackleton, the Shackleton crater, because it's deep enough and at an appropriate latitude, lunar latitude that is, where the bottom is never get sunlight, hasn't since the crater was made. And so there's thought to be ice quite a bit located in that crater because it never, gets evaporated due to the sunlight. Because otherwise, ice doesn't have the ability to stay on the moon because the intense sunlight without any atmosphere causes the ice to become H2O and then just escape into space. And it's easy to escape into space for molecules on the moon because of the moon's low mass and therefore low escape velocity. So you don't need that much energy to achieve a low escape velocity for a small body. So, where did the moon come from? So, there are 4 hypotheses that have been around in the last 100 years. Those include the fission hypothesis that the moon separated from Earth. So when Earth was forming due to the, crashing together of planetismals, maybe due to some sort of rotation rate, that just half of it wasn't as well connected and was able to separate. Okay. Another theory, or hypothesis rather, proposes that the moon formed around the Earth just as the planets did around the sun by accretion. So it was just a separate, accretion of planetismals, and it just happened to be close enough to us that we were gravitationally locked, but that it formed completely separately. Another hypothesis is that Earth caught the moon. We know of cases of captured moons, At least there are moons around other planets that highly suggest that those moons are captured moons. So this is, part of the justification for this being a hypothesis for our moon. And then the last one is the giant impact hypothesis, that the moon coalesced after a giant impact. In other words, instead of calving off when the Earth was kind of partially formed, the Earth would have been fully formed, then impacted, turned molten again, and a large amount of that material becoming the moon. I've mentioned this one before, the giant impact, and that's because it's the most likely based off of some good evidence. All right. So the giant impact hypothesis looks like this: Earth fully formed, but still primordial, right? Probably still partially molten, gets impacted by a hypothetical planetesimal, sort of a almost Martian-sized planetesimal, given the name Theia, crashes into Earth, causes so much ejecta that much of it is far enough away from Earth that instead of coming back down to the surface, it has a great enough velocity at its distance that it ended up at, that it is in a stable orbit, or at least an orbit that it can maintain and then coalesce into other material, which collectively will gain a stable orbit. So that would be the impact leading to the coalescing, and the final result being the moon. The big support of this, which is kind of mentioned here, with an activity which we won't do, which is examining the structure and composition of the moon, but which is discussed in your textbook if you read the chapter, is that, and we've even seen the numbers here in lecture. If you look at the numbers, you see that the moon is much less dense than Earth. Okay. And Earth is particularly dense, denser than any other terrestrial planets. Well, that matches really well with this hypothesis, because if this giant impact occurred, the material that became the disk of debris and then became the moon would have been material from the outer layers of Earth. It wouldn't have gone all the way down to the core. The core would have been left, affected but not ejected. So that means that the moon is just made of that lower density material, which had already differentiated to the upper layers of Earth, primordial Earth. So left Earth denser than usual, left the moon less dense than usual. And further chemical comparisons also highly support this hypothesis for where the moon came from. Part of the reason that we even need to, really speculate on this is that the other hypotheses just don't fit having such a large moon with such a relatively close orbit. Capture doesn't fit at all. No physical models suggest that there's any interaction that would lead to any plausible interaction that would lead to Earth ending up with such a large body through, just gravitational happenstance capture. So, you know, that's probably where the moon came from. Quick run through of manned lunar exploration. Okay, we had, with NASA in particular, we're just focusing on NASA here. Of course, NASA remains the only space agency to send a person to the moon, but other space agencies have been involved with, lunar exploration. And recently, there's been a lot of international lunar exploration of robotics, including from India and Japan and China. So there's been a big uptick in that. But we're just going to look at the kind of previous era of lunar exploration. And I say that because all indications, point to a renewal of exploration of the moon. You have the Saturn tests, which were testing the rockets that would later be used to go to the moon, both to orbit it and to land on it. Okay, so these are all the in the early 60s, the Saturn 1 tests, four of them. Then Gemini, okay, and the Gemini missions were manned missions that orbited the moon. And then we had another range of them throughout the 60s, which then finally led to, in the late 60s, the Apollo program. So you can think of Gemini all about orbiting the moon, which was a pretty big deal because it's way much further, way farther, way far away compared to how far we had sent, space probes, let alone people, previous to, these years. But then when we get into the Apollo missions, the goal was to land on the moon. And we get that starting with Apollo 11. So Apollo 11 was the first Apollo mission that actually had a successful landing, right? Up through mini moon landing missions, lots of people being sent to the moon. Of course, Apollo 13 was the one that didn't go so well. They had to abort and come back. Barely made it. And then all the way up to Apollo 17. And then 1974, Apollo 17 was decided to be the last one. So the planned objectives of the Apollo program have been accomplished. And then the funding year, 1974, funding is not required. NASA's official budget proposal. So they decided to stop the Apollo mission, stop spending money on sending people to the moon. They hadn't found anything that encouraged them to do so. Public interest seemed to be waning, and for whatever reason, the program was canceled. Cost $283 billion over 13 years. Was it worth it? Well, who knows? Is it worth it to go back? Why does it matter? Well, I'll let you think about that stuff. I don't think there's a right or wrong answer. It's just a worthwhile thing to think about. Okay? So quick discussion, Moon and Earth. We talked about how the best hypothesis is the collision of a large planetoid, right? Planetoid, planetesimal, those are kind of interchangeable. Sometimes you might see planetoid here because it was such a large one, so sort of a later stage, whereas the planetesimal would be a precursor. But both would be fine. Okay, we do have tidal locking, just to bring that up, which we kind of didn't touch on as much as you might expect when we talked about all the phases of the moon. And that just means that the rotation period of the moon is the same as its orbital period. And that results in one face of the moon always pointing towards us. So that's a particular type of orbital resonance that occurs when there's a lot of tidal friction between the two bodies. And that happened because of the moon's large size, close distance, and Earth's liquid oceans. Those three things combined together to result in a lot of energy exchange. And the moon would not have started tidally locked. At some point, different faces would have been showing, a couple billion years ago. But then it became tidally locked, and it's remained so, and it's going to continue to be tidally locked. And in fact, it will just slow down Earth at this point until eventually Earth and the moon will be tidally locked to each other, just like Pluto and Charon are. But the time frame for that to happen will probably never be reached because it's around 14 billion years, and the sun will have already, well, become a red giant and destroyed Earth before that occurs. So unlikely that Earth will ever become tidally locked with the moon, but it would eventually happen. if it wasn't for the sun becoming a red giant, which happens in about 5 billion years. You can show tidal locking by kind of, you know, using a pumpkin for the moon, right? Wait, the slides really like to compare the moon to a pumpkin. You hold it out in front of you with a light source, and then you just rotate it around so that it always faces you. And how do you do that? Well, you just make sure that, you know, it turns at the same rate that it rotates at, right? So that way, in the middle, you'll just always see the same face, right? So like here, and then so we have, the different parts illuminated. I'm not sure why it shows the face here. I guess that's the half illuminated. That's the new moon. Yeah. Maybe because it's too faint on the other ones. No, it just doesn't show up. But yeah, this is the new moon. Same face is pointing in each case. You're seeing the same side of the moon. So we don't see the face. I guess that's the point. Is it saying that, if you were on the other side, you could see the face. But that's the side of the moon that we call the dark side of the moon. And that side of the moon is never seen from the surface of the Earth. The first time it was ever photographed was when one of these, NASA missions flew around the backside of it. Before then, it had never been viewed in any way because you have to get behind it to see it. You're never going to see it from an Earth-based observation. All right, let's check the time here. Okay, cool. So we got about 13 minutes left. And I'm going to get through some material on Mercury. I'll be able to get through a decent amount, especially because, as I mentioned, some of the later slides get into some concepts of escape velocity and atmospheric retention, which is presented in exactly the same way that I present it in the homework. And so I'm going to kind of refer to a lot of that, as you'll see this in the homework problem. Not the one I just posted, by the way, but a homework problem that I'll be posting likely later today. So, first of all, key characteristics. Just run down with the same exact format and values that we saw for Earth. This is kind of a fun way to compare all the planets. Remember that the size and the semi-major axis are all in units that are references to Earth. So the size of Mercury is just 0.055 that of Earth. So as a percentage, you could say that Mercury has a size that's 5.5% the size of Earth. And size here is volume, right? And that's why it's so small. If you look at its radius, which would be also its diameter or circumference, because they would all have the same fraction, it's 0.38 the radius of Earth. The radius of Mercury is 0.38 the radius of Earth. So a little bit more than a third of the radius of Earth. Its density is just a little bit less than Earth's. And, because Earth's was 5.55. It's the second most dense planet in the solar system. And logically, it kind of should be the densest if it wasn't for that theory about, the lunar creation and Earth losing a lot of its low density material to make the moon, essentially, right? Thanks to an impact. And the reason that we would expect Mercury to be the densest is because of its proximity to the sun and that exposure to intense X-rays and other high energy radiation coming from the sun, essentially blasting away the surface, slowly, but gradually just breaking down the rock on the surface. And there's every indication that's an ongoing process. And so we have, a shrinking planet that's slowly getting eaten away by the sun, um, down to, denser layers and higher density material. So all the lower density material that would have been at the very crust of Mercury has been vaporized and left Mercury's orbit and actually gone into space to become space dust. The orbital period is 88 days. Okay. I want to quickly, before I talk about the semi-major axis, compare that to the rotation period, which is 58 days. So this creates a really fascinating and unusual day-night cycle for Mercury. The fact that its rotation is about two-thirds its orbit. So you can think about what that means for, you know, what part is actually facing the sun. What does it mean for the sun to rise and set when you have, such a long day compared to your year, essentially? That's what it is. Like, this is a Mercury day, this is a Mercury year. And it's pretty close. And furthermore, the fact that they're almost like make a ratio, it's almost a clean two-thirds ratio, is a form of tidal locking. It's like a partial tidal locking, like the moon is tidally locked to us. And that's because of, the tidal forces on Mercury from the sun. And so, but it's not a full tidal locking for a number of reasons. But it is that it's not just coincidental that the values almost make a two-thirds ratio. The semi-major axis is 0.39 AU. So about 40%, the distance of Earth from the sun. So you could say that Mercury is over twice as close to the sun as Earth. Because if this was 0.5, that would be twice as close. And this is more than twice as close, right? And there is virtually no orbital tilt. It's the most straight up and down of all the planets. So the orbits in rotation, which I was highlighting a minute ago, okay, are described here. Mercury completes 3 spins in every 2 orbits. Again, not exactly, but let's say approximately. Okay. So we got the spin 59 days, the orbit 88 days. I know they changed from 58 to 59, but that's because I think it's like 58.5. Okay. So what that looks like is a very interesting process in terms of what side is facing. And I highly recommend checking out this video and looking at it because it's just a fun thing to wrap your head around, and it's rewarding, and it'll help you sort of remember something interesting about Mercury in order for it to stick in your mind. And so, to have once you start, seeing how strange what a day looks like, because it's like it's not even. Their days aren't the same length because of this weird relationship. Okay. So now what about surface temperature? Well, Mercury has the greatest swings in surface temperature of the 4 terrestrial planets by far. So it has incredibly hot days that heat up to 430 degrees Celsius on the surface, and incredibly cold nights where the temperature drops to a negative 180 degrees Celsius. So incredible variation and extremes. Totally not, survivable for humans or for any known life forms. Not a place where we would expect to find, any evidence of life. NASA's Messenger spacecraft detected water ice. What? On the planet that gets so hot? And that's because of those types of shadow craters we were talking about. Okay, so polar craters are key. And having no axial tilt means that, you can just if you have a crater near one of the poles and it's deep enough, it just never gets any sunlight. So it's like just a completely isolated area. The composition is unusual in that the core is proportionally so big, which ties in nicely with what I said about much of the outer layers having disappeared over the billions of years, since Mercury coalesced in its current orbit. Okay, it's 60% metal. All right, has a solid mantle and crust, an iron nickel core, and a very weak magnetic field. So pretty like nothing significant. Its core is probably completely cooled. There's no heat left in Mercury. That's also true of the moon, by the way. These are planets that do not have molten cores. They don't have that. I mean, I guess our inner core is solid because of pressure, but they don't. They don't. Mercury does not have a molten outer core like Earth, and that's because it's just lost all of its heat to space. It's had because of its smaller size and the greater ratio of surface to volume. It's been able to cool off in the same way that, you know, if you take like, a loaf of bread out of the oven, well, like a little small one that has a lot of surface area to volume cools really quickly, but a big baked object takes a long time to cool because it's got more volume per surface area. Well, that same exact principle applies to planets. And Earth is big enough that it hasn't completely cooled, whereas, well, Mars as well, but Mercury and the moon have. There's you know, no significant internal heat left. Okay. And they point out that it has to be liquid, but I, I don't agree, I guess. I've never heard that before, that it has to be liquid. So I would not put this on a test because I don't that's not consistent with my understanding of Mercury. It is geologically dead. It doesn't have a significant enough field to suggest, anything to the contrary. And honestly, that's not terribly unusual to have, different conclusions, and they shift over time, and I'm totally, you know willing to reassess, but I haven't seen anything to make me to do that. So I would say that this is a worth looking into, but not what I know. Okay, so what the way I think of Mercury is that it is geologically dead. It's just completely cooled off. There's no tectonics, no volcanoes, no evidence of internal heat. If there's got to be a magnetic field, again, it is so weak. It is such an insignificant magnetic field that there could be easily other explanations for that magnetic field, including a permanent magnetic field that cooled into the planet. So, right there you have an alternate explanation. There's certainly evidence of past geological activity because, of course, the planet started off fully molten. And so everywhere, even the moon, right? You see past geological activity. Often the way to think about that is it's a very narrow window of time. It's just a few hundred million years out of, well, over 4,000 million years, right? Because that's 4 billion. So, you've got just proportionally an eighth or less of the entire lifespan of the planet where there was any geological activity. There was evidence of lava flows that happened in the ancient past, and um, we'll see a bit more as well. But we do have to wrap things up for today. So let's see about a good stopping point. All right. And okay. Yeah, nice explanation. I was reading that Alexander's post about like what could drive the shape of them. So it just comes down to the kinematic, so to speak, without a need of another explanation. I like that. All right. So yeah, this is what I was thinking about, other geological activity, but I won't try to squeeze it in there. That's it. What one of the defining features of Mercury, the scarps. And then so yeah, we basically just didn't get to the atmosphere, which is going to be the one that I'll briefly cover. So I'll touch on, let me actually stop the recording right now, but I'll touch on that briefly, but I'm not going to even when I touch on it tomorrow. First thing.